In classical electromagnetism, Ampere's circuital law, often simply called Ampere's law, and sometimes Ørsted's law, relates the circulation of a magnetic field around a closed loop to the electric current passing through that loop. The law was inspired by Hans Christian Ørsted's 1820 discovery that an electric current generates a magnetic field. This finding prompted theoretical and experimental work by André-Marie Ampère and others, eventually leading to the formulation of the law in its modern form. James Clerk Maxwell published the law in 1855. In 1865, he generalized the law to account for time-varying electric currents by introducing the displacement current term. The resulting equation, often called the Ampère-Maxwell law, is one of Maxwell's equations that form the foundation of classical electromagnetism. Background: until the early 19th century, electricity and magnetism were thought to be completely separate phenomena. This view changed in 1820 when Danish physicist Hans Christian Ørsted discovered that an electric current produces a magnetic effect. He observed that a compass needle placed near a current-carrying wire deflected, so that it aligned perpendicular to the wire. In a series of experiments, Ørsted demonstrated that the current could influence magnetic poles nearby and that its effect extended outward from the wire. He also observed that this magnetic influence formed a vortex around the wire. Ørsted's discovery sparked a great deal of research into the relation between electricity and magnetism. André-Marie Ampère investigated the magnetic force between two current-carrying wires, discovering Ampere's force law. In the 1850s, Scottish mathematical physicist James Clerk Maxwell generalized these results and others into a single mathematical law. The original form of Maxwell's circuital law, which he discussed in 1854 in correspondence with William Thomson, later ennobled as Lord Kelvin, and published in his 1855 paper on Faraday's lines of force, was based on an analogy to hydrodynamics. The original circuital law relates magnetic fields to electric currents that produce them and can be used to determine either the magnetic field associated with a given current or the current associated with a given magnetic field. However, it applies only in magnetostatic situations involving steady, continuous currents flowing in closed circuits. In systems where electric fields vary with time, the original law, as given in this section, must be modified by adding a term known as Maxwell's correction, see below. Equivalent forms: the original circuital law can be written in several different forms, which are all ultimately equivalent: an integral form and a differential form. The forms are exactly equivalent and related by the Kelvin-Stokes theorem. See the proof section below. Forms using SI units and those using CGS units. Other units are possible, but rare. This section will use SI units, with CGS units discussed later. Forms using either B or H magnetic fields. These two forms use the total current density and free current density, respectively. The B and H fields are related by the constitutive equation. B equals mu0H in non-magnetic materials, where mu0 is the magnetic constant. Explanation: the integral form of the original circuital law is a line integral of the magnetic field around some closed curve C. Arbitrary, but must be closed. The curve C in turn bounds both a surface S, which the electric current passes through, again arbitrary, but not closed, since no three-dimensional volume is enclosed by S, and encloses the current. The mathematical statement of the law is a relation between the circulation of the magnetic field around some path, line integral, due to the current which passes through that enclosed path, surface integral. In terms of total current, which is the sum of both free current and bound current, The line integral of the magnetic B field in Tesla's T around closed curve C is proportional to the total current yank passing through a surface S enclosed by C. In terms of free current, the line integral of the magnetic H field in amperes per meter M-1 around closed curve C equals the free current if yanked through a surface S. J is the total current density in amperes per square meter M-2. JF is the free current density only. Contour integral C is the closed line integral around the closed curve C. Double integral S denotes a surface integral over the surface S bounded by the curve C, is the vector dot product. dl is an infinitesimal element, a differential of the curve C, i.e. a vector with magnitude equal to the length of the infinitesimal line element and direction given by the tangent to the curve C. ds is the vector area of an infinitesimal element of surface S. That is, a vector with magnitude equal to the area of the infinitesimal surface element and direction normal to surface S. The direction of a normal must correspond with the orientation of C by the right-hand rule. See below for further explanation of the curve C and surface S. Nabla times is the curl operator. Ambiguities and sign conventions. There are a number of ambiguities in the above definitions that require clarification and a choice of convention. First, 3 of these terms are associated with sign ambiguities. The line integral contour integral C could go around the loop in either direction, clockwise or counterclockwise. The vector area ds could point in either of the 2 directions normal to the surface. And yank is the net current passing through the surface S, meaning the current passing through in one direction minus the current in the other direction. But either direction could be chosen as positive. These ambiguities are resolved by the right-hand rule, with the palm of the right hand toward the area of integration and the index finger pointing along the direction of line integration. The outstretched thumb points in the direction that must be chosen for the vector area ds. Also, the current passing in the same direction as ds must be counted as positive. The right-hand grip rule can also be used to determine the signs. Second, there are infinitely many possible surfaces S that have the curve C as their border. Imagine a soap film on a wire loop, which can be deformed by blowing on the film. Which of those surfaces is to be chosen? If the loop does not lie in a single plane, for example, there is no one obvious choice. The answer is that it does not matter. In the magnetostatic case, the current density is solenoidal, see next section. So the divergence theorem and continuity equation imply that the flux through any surface with boundary C with the same sign convention is the same. In practice, one usually chooses the most convenient surface with the given boundary to integrate over. Free current versus bound current. The electric current that arises in the simplest textbook situations would be classified as free current. For example, the current that passes through a wire or battery. In contrast, bound current arises in the context of bulk materials that can be magnetized and/or polarized. All materials can to some extent. When a material is magnetized, for example, by placing it in an external magnetic field, the electrons remain bound to their respective atoms, but behave as if they were orbiting the nucleus in a particular direction, creating a microscopic current. When the currents from all these atoms are put together, they create the same effect as a macroscopic current, circulating perpetually around the magnetized object. This magnetization current Jm is one contribution to bound current. The other source of bound current is bound charge. When an electric field is applied, the positive and negative bound charges can separate over atomic distances in polarizable materials, and when the bound charges move, the polarization changes, creating another contribution to the bound current, the polarization current Jp. The total current density J due to free and bound charges is then J equals Jf plus Jm plus Jp, with Jf the free or conduction current density. All current is fundamentally the same, microscopically. Nevertheless, there are often practical reasons for wanting to treat bound current differently from free current. For example, the bound current usually originates over atomic dimensions, and one may wish to take advantage of a simpler theory intended for larger dimensions. The result is that the more microscopic Ampere's circuital law, expressed in terms of B and the microscopic current, which includes free, magnetization, and polarization currents, is sometimes put into the equivalent form below in terms of H and the free current only. For a detailed definition of free current and bound current, and the proof that the two formulations are equivalent, see the proof section below. Shortcomings of the original formulation of the circuital law. There are two important issues regarding the circuital law that require closer scrutiny. First, there is an issue regarding the continuity equation for electrical charge. In vector calculus, the identity for the divergence of a curl states that the divergence of the curl of a vector field must always be zero. Hence nabla times B equals 0, and so the original Ampere's circuital law implies that nabla J equals 0, i.e. that the current density is solenoidal. But in general, reality follows the continuity equation for electric charge. Nabla J equals minus del rho del T, which is non-zero for a time-varying charge density. An example occurs in a capacitor circuit where time-varying charge densities exist on the plates. Second, there is an issue regarding the propagation of electromagnetic waves. For example, in free space, where J equals 0, the circuital law implies that nabla times B equals 0, i.e. that the magnetic field is irrotational. But to maintain consistency with the continuity equation for electric charge, we must have nabla times B equals 1C2 del E del T. To resolve these situations with that above, the contribution of displacement current must be added to the current term in the circuital law. James Clerk Maxwell conceived of displacement current as a polarization current in the dielectric vortex C, which he used to model the magnetic field hydrodynamically and mechanically. He added this displacement current to Ampere's circuital law at equation 112 in his 1861 paper on physical lines of force. Displacement current in free space. The displacement current is related to the time rate of change of electric field. In a dielectric, the above contribution to displacement current is present too, but a major contribution to the displacement current is related to the polarization of the individual molecules of the dielectric material. Even though charges cannot flow freely in a dielectric, the charges in molecules can move a little under the influence of an electric field. The positive and negative charges in molecules separate under the applied field, causing an increase in the state of polarization, expressed as the polarization density P. A changing state of polarization is equivalent to a current. Both contributions to the displacement current are combined by defining the displacement current as JD equals del TD, RT, where the electric displacement field is defined as D equals epsilon 0 E plus P equals epsilon 0 epsilon R E, where epsilon 0 is the electric constant, epsilon R the relative static permittivity, and P is the polarization density. Substituting this form for D in the expression for displacement current, it has two components. JD equals epsilon 0 del E del T plus del P del T. The first term on the right-hand side is present everywhere, even in a vacuum. It doesn't involve any actual movement of charge, but it nevertheless has an associated magnetic field, as if it were an actual current. Some authors apply the name displacement current to only this contribution. The second term on the right-hand side is the displacement current as originally conceived by Maxwell, associated with the polarization of the individual molecules of the dielectric material. Maxwell's original explanation for displacement current focused upon the situation that occurs in dielectric media. In the modern post-ether era, the concept has been extended to apply to situations with no material media present, for example, to the vacuum between the plates of a charging vacuum capacitor. The displacement current is justified today because it serves several requirements of an electromagnetic theory: correct prediction of magnetic fields in regions where no free current flows, prediction of wave propagation of electromagnetic fields, and conservation of electric charge in cases where charge density is time-varying. For greater discussion, see displacement current.